All right, good afternoon, everyone. Welcome to coming to my first ever conference talk. It's called From C Extension to Pure C. And it's a story of how my team and I migrated RBS from being a Ruby gem with a C extension to a Pure C library. Let's jump into it. First, I'll introduce myself. My name is Alexander Momchilov. I'm a staff developer at the Ruby Developer Experience team at Shopify. I flew in from Toronto, Canada, and I'm actually one of 3 different presentations that my team is giving this year about type checking and static analysis. Yesterday, my coworker, Vinicius Stock, presented Embracing Ruby Magic, statically analyzing DSLs. And that was yesterday. So you can either jump in your time machine, go back and see it then, or you could just wait about a month to see the recording. There's this talk now, and tomorrow, my coworker, Alexandra, is presenting inline RBS comments for seamless type checking with sorbet. And that's in the same hall tomorrow at 14 o'clock. And so yes, there's actually 2 different Alexes presenting RBS-related talks just for my team alone. And if your name is also Alex, we're hiring. You can join and make an RBS talk of your own. Now, just kidding. Any name can apply. Shopify is always looking for exceptional talent. So if you're interested, please scan the QR code. I'll leave it up for a moment longer. But let me get into what is RBS and what are we going to talk about today. So in short, RBS stands for Ruby Signature. And it's a standard notation for describing the types of various constructs in your code. So you can annotate what you expect the types of your local variables, instance variables, method return values, parameters, and so on to be at runtime. Originally, RBS was written in separate .rbs files. These are files that aren't executed by the Ruby virtual machine. They're not even seen by the interpreter at all. Instead, they're sort of exist in parallel in your same repo for static analysis tooling to read, not for your actual Ruby code to execute. Inline RBS was a sort of development that let you write the same RBS signatures that you had in your RBS files, but now inline in your RB files into comments. I'll show you examples of both of these. When your programs have RBS signatures in them, you can use a type checker to automatically validate the correctness of your program and to make sure that all the types line up. If you're passing a string to some function that expects an integer, it will tell you that something went wrong. So let me give an example of some RBS files and how RBS inline improves upon that. So this is an example RBS file that you'd note is called message.rbs. Like I mentioned earlier, the Ruby interpreter will never see this code. Even though it looks a lot like Ruby, it's not actually Ruby. It just sort of follows the same flavor. You'll notice these methods don't even have bodies. They don't even have an end keyword at the end. Instead, it uses this colon to denote the start of a type annotation. So we have some attribute readers here for some attributes of the message class that have a type user, string, optional message. And then functions are annotated with this arrow notation to say what arguments they take and what return values they return. Now you can imagine why this would be pretty cumbersome to sort of keep in sync. When I rename my message class, or perhaps I call reply2, I would have to rename it in both my real Ruby code and then update the RBS as well. And that's just not a good developer experience. Inline RBS improves upon this by taking those same signatures and stuffing them into comments. The Ruby virtual machine just thinks that these are regular old comments, but static analysis tooling can look for the special colon that comes after the hashtag to know that this isn't any old comment in English. This is a comment that's meant to be in an RBS format. And so now this would be the one file that you would have in your repository. You don't need a separate RBS file. And you can have your real method implementations. You see now there's method bodies with end keywords and so on. And you can see it's the same syntax as before. So why were we interested in RBS? We don't actually use the main type checker for RBS, Steep, at Shopify. Instead, we use Sorbet, which has this really cute cone mascot, which is a static type checker that's written in C++. So it's blazingly fast. It's also really highly memory optimized, so it scales to the needs of our really huge monolith. Sorbet is able to type check about 9 million lines of our main monolith in under a minute. It's actually really impressive on the performance front. So our team liked the Sorbet type checker, but we wanted to replace the Sorbet SIG syntax. The SIG syntax is a Ruby DSL that is how Sorbet code expresses the types instead of these RBS comments. And that's all you could use up until today. Because it's a Ruby DSL, it involves actually calling methods that need to exist at runtime. And they're provided by the Sorbet runtime gem. This was a big limitation. If you were a library author and you wanted to use Sorbet signatures to improve the resilience and robustness of your code, you would not only have to use Sorbet runtime in your own development of the gem, but you would also force all the consumers of the gem to also depend on Sorbet runtime indirectly. And that's just too tall of an order. And it's something we wanted to fix. Also, we found that SIGs in the sorbet syntax are really verbose and clunky. And let me show you an example of that. On the left here, we have a point class that is expressed, that has its types expressed using RBS comments. And on the right, we have the exact same material expressed using sorbet SIGs. You'll notice that you have all these method calls to SIG, which are passed a block. And within that block, various DSL methods are called, like params and returns, given various type objects as parameters. The SIG method has to actually be called at runtime, and that's where you see this extend tsig module being extended. And this has a runtime representation that we would like to get rid of, ideally. So what did we want to do? Well, we wanted the brilliant, like, Dragon Ball Z fusion of RBS and sorbet together. We want to have the sort of elegance and terseness of the RBS syntax, but we wanted to keep sorbet as the fast and performant backend type checker that's going to actually consume these comments and do something with them. So that's exactly what we've done. Here's a quick little demo where we have a method called should return a string. It takes an integer, it returns a string, as the sorbet SIG very verbosely explains. And you see we just call i.toS, there's no complaints. Now, if I change this and I replace it to just be a number, you'll see immediately that the sorbet LSP jumps in and says, like, hey, we expected a string, but you gave me a number. I'll change it back to a string, and we're OK again. Change it to a number. Oh my God, we can't have a number here. It needs to be a string. Now, if I remove this sorbet signature and I replace it with an RBS comment, you'll see that when I change the code below, we get the exact same type errors as below. Woohoo! Change it to a string, it works again. The really great part is that we don't need to extend tsig, and we don't even need to use the sorbet runtime gem. We can remove the requires, and we can even remove it from our gem file, because we're no longer calling methods in a Ruby code anymore. And there's an open pull request to merge our work, which we're hoping to have landed really soon. We're already sort of experimenting internally at Shopify. So what was so hard about this? What warrants making a conference talk about the work that we've done here? To explain that, I'm going to have to give a really brief overview of the history of RBS and how it was sort of developed. Before 2022, RBS. RBS was a pure Ruby gem that had an internal parser that was written in Ruby that was accessed via a regular old Ruby API. You would call the parse method on RBS parser. In 2022, Sotaro rewrote the internal implementation of this parser to use a C extension. So now you still have the same Ruby API, but now implemented with a C extension in the background. Of critical importance is that this C code still makes very heavy use of Ruby VM features from the C extension API, and that's something that we're going to need to address, and I'll get into why. Our work was to take this a step further and make it so that this is a pure C parser that does not use the Ruby extension APIs at all. So while the Ruby VM still exists like the Ruby API exists like it was before, and Ruby apps can call it, we now have this new C API. So let's look at what this achieves. Existing users of RBS, such as Ruby LSP, which is the tool that powers the rich editor integrations into your IDE, and type checkers like Steep, can continue to use RBS as if it were a regular Ruby gem, and they'll just call regular Ruby methods. But what we've unlocked is for tools that don't want to necessarily call Ruby code to be able to make use of RBS as a library. And so, for example, we'll have a new type checker, or a different type checker like sorbet, which is written in C++, and even alternative Ruby runtimes like JRuby can make use of this. And they can just make calls to the C code. The JRuby example is a particularly good one, where JRuby can handle Ruby gems that just have Ruby code. It can also make foreign function interface calls into C libraries, but Ruby gems with C extensions are this middle ground that it can't support, and we fixed that for this context. So why was the Ruby dependency a problem? Well, the first problem was that using any of these Ruby features of the Ruby VM requires holding the global VM lock. When you do that, you limit your CPU parallelism to just a single thread unless you start to incorporate ractors. And this was going to be a really big issue for us because one of the ways that sorbet is able to be so fast is that it can parse all of your files in parallel on multiple threads within the same process. If we're using RBS as a Ruby gem, the JVM would just limit the parallelism of that down to just a single core doing real work at a time. Another thing to note is that, like I mentioned earlier, MRI's C extension API is not portable and would preclude alternative Ruby runtimes from being able to use the API. And lastly, there's also a peripheral benefit around performance, where with C code we have a bit more control over the memory layout of things, and we can tune things to use less memory and less CPU. So if there's all these benefits, one might ask, why was RBS using Ruby in the first place inside of its rewritten C parser? Why didn't it just use pure C code from the beginning? Well, the reason is that the Ruby VM is really convenient. It gives us a lot of really great features that we're going to have to give up and replace. The first of these is error handling via exceptions. C doesn't have exceptions, so we're just going to need to do something else. The next is memory management. So the Ruby VM provides a dynamic memory allocator and a garbage collector that will take care of freeing memory for you when you're done using it. And so we're going to need to do something about that. And there's two more points that I'll mention that I won't elaborate as much. The first that you might be familiar with is that the Ruby standard library provides us with a lot of really convenient classes and data structures. You can think of array, hash, there's queues, and so on. So we're going to need to find replacements for those. One suggestion that I'll make here is that we should resist the temptation to just hand roll all our own data structures. I would really recommend trying to use well-tested, high-performance container libraries that exist for C code. And lastly, I'll mention that Ruby, as an object-oriented programming language, gives us polymorphism. We can have methods that are dynamically dispatched, so that when we send a message to an object, the Ruby VM will automatically figure out for us what's the class of this object and what's the correct implementation of that message for that object. So let's dive into the first two of those in detail. The first Ruby convenience is error handling. So idiomatic Ruby code handles errors via exceptions. And this is really great. When we raise an exception, it's like a kind of deep return. Like a return statement, we're going to stop the execution of a current function. But unlike a return statement, it has this deep quality where we can actually jump multiple layers of the call stack. If we will interrupt the parent function and the parent's parent function and so on, all the way up until we reach the most recent rescue block. It's like a kind of teleportation that we can do. The Ruby C API exposes these with APIs like RBRaise and RBRescue. So let's see an example of how that might have been used and what we'll do instead. Here we have a fictional function called parse optional tuple. A tuple in RBS is just a fixed length array of potentially different types. So for example, you might have a tuple of a string, an integer, and a bool that can be packed together. An optional tuple is just a type that describes either those things or nil. So you could have either value be passed to a parameter of this type. So we'll see that to parse an optional tuple, well, first we're going to parse a tuple, and then we're going to see, is it followed by a question mark? If it is, then we have an optional tuple. If it's not, we have just a regular tuple. Looking into the implementation of parse tuple, we'll see that one of the first things we're going to want to do is assert that we have an opening square brace as the first character. If we don't, then this isn't a tuple, and there's just some kind of syntactic error. And so this RBRaise over here that we do that raises syntax error, well, that's a Ruby feature, and we won't be able to use that. So how do we throw exceptions without Ruby? That's the cool part. You don't. We're just going to need to figure out something completely different here. So we know that RBRaise has got to go. We can't keep that. What we'll do instead is we'll return false. Like I mentioned, you could think of raising exceptions as a kind of deep return. So we could just return a bunch ourselves. So we're going to return false in this case, and false means that an operation failed. Likewise, if we get to the end of this function and we succeed, we're going to want to return true, and true says that the operation succeeded. But to do this, to be able to return booleans where previously we would be returning these RBS nodes, we're going to have to change the signatures. It's going to be a little inconvenient, but we can go through it. So we'll take the RBS node pointer return types, and we're going to actually move them into the parameter list as out parameters. And the actual return types are going to be bool. What this means is that these functions are going to return a value not by actually returning it, but by storing it into a location of your choosing. When we do this, we'll no longer be able to call parse tuple in the way that we do near the top here, because its return value is just going to be a Boolean, not the node that we're looking for. So we're going to move it onto its own line, and we're going to pass to it the local variable into which we want parse tuple to store its result. But now we have to ask the question, did this succeed? And to know that, we have to check the Boolean that was returned when this function was invoked. So we'll wrap this in an if statement, and we'll say if not parse tuple, so if the result is false, then we know that we have an error condition. And what do we want to do in this case? Well, we're going to return false, which is a sort of form of manually bubbling up an error. So a key note here is that error propagation is manual, and it's kind of inconvenient, but that's just what we're going to have to do here. Now, to fill in a few more details, you'll notice that, well, we can only return Booleans from these functions, so this long return value here is going to be an issue. So what are we going to do? We're going to assign it to our out parameters. We're going to move over that expression, and we're going to turn true for success at the end here. And so that's an example of how the error management in one of these libraries might look like. Next, I'm going to talk about the second convenience that Ruby provides us, which is memory management. And I'll talk about it through an example. So suppose we have a foo, which is some kind of syntactic construct that involves, to parse a foo, which involves parsing A, then parsing B, then parsing C. These are just all examples. Now, if we get midway through the process and we encounter syntax error, there's no reason for us to keep trying to parse the whole rest of it. We want to bail early. So let's add some early guard clauses that will return if any one of these steps fail. And let's briefly walk through the happy path of what would happen when we call this code. To do so, I'll bring up a little representation of a runtime stack on the right here, and we're going to step through it like a debugger. So when we enter our function, we have an execution pointer that's going to look at the start of our first line. And we have a call stack, or a stack frame allocated in our call stack, which has uninitialized variables with for local variables called A, B, and C. When we call parse A, internally it's going to parse our text. It's going to allocate some result object A. It's going to return the pointer to it. And we're going to assign that pointer into our local variable A. Similarly, we'll call some function parse B. It's going to parse some stuff, capture that data in a B object, and we'll point to it. Lastly, we'll do the same for an object C. So all this parsing succeeded. And what we want to do is package up this data together. So at this point, ownership over these objects belongs to the stack frame of our current function call. But when we create a new foo object, it's going to have pointers to those three objects. And when we return the foo object out of our current function call, our stack frame is going to disappear, and with it, the pointers that we had to those objects. This all works great. Whoever is going to own the foo object after this function call is going to be responsible for not just freeing the foo, but also freeing its constituent A, B, and C. But now let's see how this can go wrong if you have an error. Again, we're going to enter our function, allocate a stack frame, and we're going to step through it. Suppose parsing the A succeeds. We're going to get some A object on the heap, and we're going to point to it with our A local variable. But now let's say that there is a character that's out of place for our B value that we don't even allocate it because we just can't. We don't know what the syntax is that we're trying to parse there. It's going to return null. We're going to store that in a local variable. And on the next line on the if statement, we're going to decide to return early. At this point, our stack frame is destroyed. The local variable A stops existing. And our object A is still there. We haven't freed it. So this object exists on the heap, but there's no way for us to access it anymore, not either to use it or to get rid of it. It's almost like a helium balloon. If you hold onto the string of a helium balloon, it's yours. You can use it, you can have fun, and you can throw it out. But if you let go of the handle of your helium balloon and you have no other strings attached to it, it's going to fly away and you lose control over it. This is what we would call memory leak. And so A has leaked. Now, if you just leak one object occasionally, it's not great, but it's not the worst. But it's interesting to note how this works in the case of RBS. So you might just start writing some partial RBS code because your code isn't always syntactically valid as you're typing it. You're starting on the left and you're typing character by character, and almost every time that your IDE is going to parse this code, it's not going to be valid. So we might start with an empty comment, then we might open a brace, but that just leaked some objects. And then we're going to say, well, there's a parameter x and it's an integer and we're leaking objects, and there's also a y, and oh god, there's a lot of objects, and it's going to return void, and there's more objects. And eventually, your IDE will get killed by the operating system because you use too much memory if your leaks are too bad. We don't want this. So how do we fix it? Well, the manual way to do it is going to need a bit more room. So I'll move this code over, and I'll add some more lines for us to use. And we are going to need to add these free calls. So let's see how they help. If we just look at the first segment of this where we parse an A, we don't have anything to clean up. If parsing A fails, then there's no other objects that we need to free, so we could just return null. There's nothing to do here. If parsing A succeeded and we got to parsing B and the B failed, well, when the B fails, we've already successfully allocated the A. And so we're going to need to free just the A, but not the B. Now, supposing parse B succeeded, now there's the free A. Supposing parse B succeeded and we moved on to parsing the C, well, at this point, the A and the B were allocated, but not the C, so we're going to need two free statements. And so what you can see here is that the number of different free calls that you have to add scales pretty unfortunately with the number of exit points and local variables that you have in your function. And because we use early returns as a way of modeling errors, that introduces even more areas where we early return and need to do manual cleanup. And so not only is this quite unpleasant to program, but it's really error prone, and you risk either forgetting to free a resource, which means they have memory leaks and potentially eventually out of memory crashes, or potentially you double free the same object, you free it twice, and you have undefined behavior. At best, you might have it crash immediately. At worst, you might have subtly wrong behavior in your library, and it's going to be really hard to debug. So to fix this, let's talk about memory allocators. Now, the C standard library provides a memory allocator that you're probably quite familiar with, and it's exposed through malloc and free. Malloc has a deceptively appealing and simple-looking interface. You give it a number of bytes of memory that you want, and it returns back either null if there's no memory, or a pointer to a chunk of memory with at least that many bytes available for you to use. You use it for as long as you'd like, and when you're finished with that memory, you pass that same pointer to free, and you're done with it. Now, the problem here is that object lifetimes are just too granular. Like you saw in the previous example, we have all these sort of related allocated objects that are sort of spawned around the same time, but we have to deal with them in this really fine-grained way, which is error prone. And it also has a performance cost because we're making so many separate calls to free. And if there's one takeaway that I can drive here is that even though malloc and free is universal across the C standard library, and it's so approachable, it actually makes it really difficult to make leak-free and robust code. So the core idea that we want instead is to think, what if we group objects of similar lifetimes together? We want something that lets us allocate objects at similar but different times, but then we can free them all at once. So a really simple example of this is if you have a Super Mario world. As you start world 1, you'll go through, some objects will get allocated for the Goombas and the shells and the level and the Mario himself. But when you go down the exit pipe, everything for that level can be deleted. You don't have to worry about, is it the first Goomba or the third one? Everything can go at the same time. Similarly, in our RBS case, we allocate a new RBS parser for every single signature that we parse. And whether we succeed or fail, we could just clear the whole thing at the very end, and there's nothing to worry about. So that's an example of how these two sort of standard and custom allocators could look like. On the left here, you'll see these calls to malloc, where we ask it to allocate enough memory for the size of an integer, a character, and some foo t structure. It will return back the pointers that we wanted, and we can call some doThing function, the proxy for the work that we want to do with those objects. At the end, we'll free each of them individually. And so you see, those are quite a few function calls. Internally, they could do a fair bit of work. And so there's a performance cost to that, and it's easy to miss one or get it wrong. On the right, we have similar code that does almost the same thing, but it uses this custom allocator that we call an RBS allocator. We initialize an allocator with a predefined amount of memory that we know is going to be enough, in this case 4 kilobytes. And when we call RBS alloc, we pass in the instance of the allocator with which we want to allocate the memory. And again, it will return pointers to us that we use almost in the same way as malloc. We do something with them, but crucially, when we finish with them, we don't free those pointers individually. Instead, we could just wipe away the whole allocator in one shot. And so you can imagine you have an array of thousands of objects, and rather than looping through the array and freeing each one independently, you can just drop the whole thing. So let's visualize what happens inside one of these allocators. You'll hear the term arena allocation, or also perhaps slab allocation. It's a similar idea, but it starts with getting this big piece of memory and having a pointer that just keeps track of where your most recent free slot is. Every time an allocation is requested, you're just going to put it where the free spot was and move the free spot along. And so we might allocate some objects, A, X, B, and they're all going to live in here. Now, for our allocator, we chose to make it really simple because we know that RBS parsers are very short-lived. They're allocated and dropped within like a millisecond. So we don't have to worry about doing any complicated work about freeing objects and finding holes to allocate them in. So if somebody stopped using X, we could just leave it as it is. That will be unused memory. It's going to be wasted for the lifetime of the allocator, but because this one isn't going to live so long, we don't have to worry about it. Now, when we allocate C, you see that we don't actually fill C where X was. We'll just keep allocating at the end. It's simpler that way. So we can keep on allocating here. We have some object Y. Maybe we finish with Y. Here's our foo. Maybe we'll have some other objects to allocate, and so on. Now, a cool thing here is that this allocator lets us have objects that point amongst each other in any which way. So like before, our foo can own an A, a B, and a C. And these pointers can have cycles, they can be transitive, like we don't have to care. The really cool part is that when we're done with it, we could just drop the whole thing. We don't have to chase the graph, make sure we don't get caught in loops. We just wipe away everything. There's a risk to it though. If I revive back that memory, I showed you here pointers that are within, between objects within the same arena. But if you have objects from one arena pointing to objects in another arena, or for example, if you have local variables or global variables pointing into an arena, you'll have these external references from outside that point into it. And if you drop your arena at the wrong time without cleaning those up, you get dangling pointers. Any attempt to read or write from these memory locations is going to blow up. Again, in the best case, it's going to crash your program immediately. In the worst case, you're going to have really subtly incorrect behavior. It's going to be hard to debug. Now let's look at how this lets us write the code that we wanted. We have a similar example to before, where we have all these early returns. But within the parse A, B, and C functions, we'll note that everything is allocated, owned by a particular allocator for this current parser. And because that parser owns all those objects, and they'll all be freed at the end, whether we succeed or we fail, we don't have to worry about any manual cleanups on the early return paths here. And so this is much easier to get right. There's nothing to do. There's another downside that I'll mention, which is that when you have functions that need to allocate, they need an instance of the allocator to allocate with. And so here's some example functions. We have a RBS hash new, RBS list new, some function to unquote a string and to strip the white space off a string. Well, for them to be able to allocate internally, we're going to have to add a new parameter. And plumbing these around can be kind of annoying. Basically, almost every function in your system is going to take one of these, and almost every function call is going to involve passing it. It's a little tedious, but there's a kind of a cool upside, which is that at a glance, I can tell you that RBS string strip whitespace doesn't allocate. I can tell you that it's not going to return me a copied string of the whitespace trimmed off. It's going to give me a string that points into the same memory with the start and the end chopped off without doing any memory allocation or copying. That's pretty awesome. So in summary, what's the big deal about extracting a C library from a Ruby gem? Why would I want to do it? Well, pure C libraries are just more portable than Ruby gems that contain C extensions. Because we're not calling Ruby anymore, we don't have to Ruby about the global VM lock, and we could just use any kind of threading that we want without being limited by it. I would recommend that you establish a consistent pattern around error handling early on in the process. Like I showed, it's going to mean that, for example, your functions return booleans, and that's going to impact your API design, and it's pretty hard to retrofit that once you've already built up a big system. Similarly, I suggest you think about lifetimes really early in your design and implementation, because you're going to need to pass around allocators, and it can be really frustrating to decide, oh, actually, I need an allocation here, but this function doesn't have an allocator, and the function that calls it doesn't have an allocator, and now you have to go get your plumbing tools and start wiring allocators through everything. That could be quite difficult. And again, I would recommend that you embrace popular libraries for fast and well-tested containers. There's a bunch of those for C, and try and make use of those where you can. To learn more about the benefits of RBS and what you can do with it, I would recommend you join my colleague Alexandra tomorrow in this same hall at 14 o'clock for his talk, Inline RBS Comments for Seamless Type Checking with Sorbet, in which you can learn more about how Shopify is adopting RBS in our code and our tooling. And lastly, I would really like to thank Alexandra, Stan Lowe, and Sutaro for their work on RBS and for the great success we've had so far. Thank you so much. That's all, folks.